In this video lesson, we are going to study the periodic table and periodicity. Here we will cover properties like the atomic radius, ionic radius, ionization energy, melting point, first ionization energy, melting point, and electrical conductivity. Before that, please, if you are not subscribed to our video, like this video and subscribe to our channel. Do not forget to hit the notification bell. Welcome back. As I earlier said, today we will be covering the periodic table and periodicity. And what do you understand by periodicity? Periodicity. And for purpose of the limitation of the syllabus, we'll be working mostly on period 3. Period 3 and period 2. Period 3 and period 2. So what do you understand by periodicity? Periodicity, as the word implies, this is the study of periodic trends. Study of periodic trend across the period of the periodic table. We are talking of repeating patterns in the physical and the chemical properties of elements across the period of the periodic table. As I said, we will cover things like covalent radius, metallic radius, atomic radius, and ionic radius. Another interesting area is covalent radius. What is a covalent radius? A covalent radius, as you understand, the covalent radius is half the internuclear distance. This is half the internuclear distance between two adjacent non-bonded atoms. And atomic radius is the distance between an atom's nucleus. The distance between an atom nucleus and the outer electron shell. Ionic radius, on the other hand, is the distance between the nucleus and the electrons in the outermost shell of an ion. So precisely, if you look at the periodic table, the periodic table has been modified as seen here. It's no longer group 1, we start from group 1, group 2, group 3, group 4, group 5, group 6, right to group 18. Even the D block elements have been given groups. So we are the highlighted areas, period 2 and period 3. These are the places we are going to focus our discussion. If you look at the property here, you will realize that atomic size will increase as you go from right to left. In other words, we are saying that the atomic sizes are decreasing as you go from left to right, or increasing as you move from right to left. electronegativity too are increasing as you move from metals to non-metals. Ionization energy is also increasing as you move. There's a consistent increase as you move from metals right to noble gases. Atomic size, on the other hand, as you move from top to bottom of the periodic table, the atomic size is increasing because of the increase in the number of shells due to increasing number of electrons. Then electronegativity, on the other hand, is increasing as you move from bottom to top. Ionization energy is also increasing as you leave from bottom to top because of what? Electrons are becoming closer. The valence electrons are becoming closer to the nucleus. Now, again, let me show you this variation. As I said, in atomic radius, as you move from metals to non-metals, the highlighted area in green, what is happening is that there is a consistent decrease in the atomic radius as you are moving from metals to non-metals and to the noble gases. And as you go down the group, you see the atomic sizes are also increasing. Like as I said the other time, atomic radius, I said it is the distance between an atom's nucleus and the outer electron shell. There's it here. From the nucleus of this hydrogen molecule, from the nucleus of the hydrogen atom to the outer electrons, that distance from the outer electrons to the nucleus is what we call the atomic radius. Now, we want to look at variation. We want to look at the variation in the atomic radius. Variation in the atomic radius are in period 3, from sodium to argon. You will see that there is from the curve, you will see that the atomic radius is decreasing from sodium right down to chlorine. There is a general decrease in the atomic radius across the period, a decrease. So there are a number of reasons for that. We said as you move across the period, there is a general increase in the positive nuclear charge, which is resulting from increasing number of proton. So as the nuclear charge is increasing across the period, what happened? There is an increase in the attractive force between the valence electron and the nucleus. As a result, the outer electron or the valence electron are pulled towards the nucleus, reducing the atomic radius. So this is what is happening there. Then there is another property here there is another property here, which is variation in the ionic radius. I said the ionic radius, this is the distance between the nucleus and the electrons in the outermost shell of an ion. Distance between the nucleus and the electron in the outermost shell of an ion. So we have sodium ion, magnesium ion, aluminum, silicon, phosphorus, anion, sulfur, chloride, and the noble gas argon. So you see that there is a consistent decrease in the ionic radius. The reasons are simple. Look at the graph here very well. If you look at the graph here very well, you will see that the ionic radius from metals, it goes right down. It is decreasing. There's a general decrease in the ionic radius of metals, right down to silicon. Of course, silicon is regarded as a metalloid, a semi-metal, as a metalloid. So the ionic radius decreases right to silicon, then rises right up when they start with the anions, phosphorus anion. So now you see that it rises right up there and start and decrease gradually. The decrease is not really significant, just gradually like that. There is a reason for this curve. There is a reason for that. So again, you can see this for ions here. Let me just use this as an example for you to show. You will see that here from sodium ion to magnesium to aluminum, there is a general decrease in the cation size. The ionic size of the cation are decreasing. Then for the anions, you see that they are decreasing, but it is not really significant. From 212, 184, and to 181. The decrease is not really significant compared to the one in cation. And now we can explain, we can now say that the variation from sodium, I can now say that sodium to silicon going across the period, the cations are much smaller than their atoms. The cations are much smaller than their atoms in size. From sodium to silicon, the cations are more smaller. So if you compare the sizes of sodium right to silicon compared to their atomic sizes, these ionic sizes to the atomic sizes, you will see that the cations are much smaller than their atoms. Why? Because they have effectively lost their outer shell of electrons. Because they have lost their outer shell of electrons, that is, since they are period 3 elements, that is the third principal quantum shell or energy level. They have lost their outer electrons in the principal quantum shell. Then these cations, again, there is less shielding of the outer electrons in the cation compared to their original atoms. One reason is that their decrease is that they have lost their outer shells of electrons. That is, the electrons in the third principal quantum shell have been lost. Secondly, there is less shielding of the outer electrons in the cation compared to the original atoms. Therefore, we can now conclude that going across a period from sodium ion to silicon ion, the ion gets smaller because the increasing effective positive nuclear charge exert a greater force of attraction on the outer shell electron, pulling them closer to the nucleus. That's all. From all this information, I said you can conclude that going across the period from sodium ion to silicon ion, the ion gets smaller because the increasing effective positive nuclear charge exert a greater force of attraction on the outer shell, pulling them closer to the nucleus. That's okay. Then again, if I want to now for the anions from phosphorus P3 minus right to chlorine Cl minus, we can now say for the anions, we can now say going across the period from the phosphorus anion to the chloride anion, going from phosphorus anion to the chloride anion, the negatively charged ion are larger than their original atoms. Cations are smaller than the original atoms, but these ones here are larger than the original atoms. The anions are larger than their original atoms. The reason here is because each atom has gained. Each of the atoms from phosphorus to chlorine has gained one or more extra electrons into their third principal quantum shell, increasing the repulsion between its electrons, whereas the nuclear charge still remains the same. Once more, the reason why these ions, the anions, have greater sizes more than the atom is because I said each atom have gained one or more extra electrons into their third principal quantum shell, increasing the repulsion between its electrons, whereas the nuclear charge still remains the same. That's right. It takes us to another property here, which is ionization energy. Ionization energy. The first ionization energy here we say describe and explain the trend in the first ionization energy across the period. Fellow learners, it is obligatory to know the definition of the first ionization energy. You can use this to define what you understand by the first ionization energy. The first ionization energy is the energy required to remove 1 mole of electron. Energy required to remove 1 mole of electron from 1 mole of gaseous atom to form 1 mole of gaseous ion with a unipositive charge. Then again, if it was the second ionization energy, you could be asked to define. If it was the second ionization energy, you will say the energy required to remove 1 mole to remove this 1 mole of the second electron. Here it will be 2e, not 1e. It will be 2 electrons from 1 mole of gaseous atom, forming what? Forming 1 mole of gaseous ion with what? With a 2 plus charge. It will be 2 electron, 2 plus charge. And you must mention the gaseous state of the atom. You must mention the gaseous state of the ion. And you must show that they are all 1 mole. Back to the property. If you look at the first ionization energy of the elements, or the first 20 elements, the ionization energy is a property that has been plotted against the atomic numbers. You will see that from hydrogen to helium, this is period 1. From lithium at the bottom here to neon, that is period 2. From sodium here at the bottom here to argon, that is period 3. Then from potassium to calcium here, that is period 4. That is the consistency in the pattern. It is we call it a property because you see the ionization energy is in a repeated. It has a repeated pattern across the period. You see, there is a general increase, or there's a general increase across the period. There is a general increase from lithium here across the period. There is a general increase here from sodium across the period. And there is a general increase here that is living from sodium across the period. So that is why we call it. That is why we call it a property. So now, in this property, you will see that even though there is a general increase in the first ionization energy across a period, like from lithium to neon, and from sodium to argon, there are some groups with exception. We are talking of group 13 and group 16. If you look at group 13 and group 16, okay, this is group 13 and group 16. Let me take you back there. There is group 13. Group 13 is here. On group 13, we have boron, we have aluminum. On group 16, we have oxygen, and we have sulfur. Then group 15, we have nitrogen, and we have phosphorus. If you look at the ionization energy, you will see that there is a pattern there. After beryllium, there is a drop in the ionization energy to boron. From beryllium, there is a drop to boron. Again, after nitrogen, there is a drop in the ionization energy. Let's go to period 3. In period 3, after magnesium, there is a drop. After phosphorus, there is a drop. We will have to give reason why there is a consistent drop after some of these elements. So we can now say, there is a general increase in the first ionization energy across the period because the increasing nuclear charge and the decreasing atomic radius, makes the attractive force between the nucleus and the outer electron greater. The only exception are group 13 and group 16. I said there is a general increase in the first ionization energy across the period because the increasing nuclear charge and decreasing atomic radius makes the attractive force between the nucleus and the outer electrons greater, except for group 13 and group 16. Then we may have to explain why there is a drop. There is a drop after beryllium, there is a drop after nitrogen, there is a drop after magnesium, and there's a drop after phosphorus. These are the explanation. There are small drops in the general trend across the periodic table, magnesium and aluminum, between phosphorus and sulfur, and in period 3 as well as in between beryllium and the boron and nitrogen and oxygen in period 2. The drops between beryllium and aluminum. The drop between beryllium and boron, and as well as magnesium and aluminum. Let me explain the drop between beryllium and boron. I told you in an exam, when you are given, why is it that this one has an ionization energy, the first ionization energy of boron? They can say, why is that the first ionization energy of boron is less than that of beryllium, as seen here? Why is it that the first ionization energy of boron is less than that of beryllium? Or they can say, contrary to the consistency in the rise in the ionization energy, there is a drop after beryllium. Explain why. Or they can say, why is it that boron has a lower first ionization energy than beryllium? And this is the reason. When you have a question like this, learners, the first thing you do is write the electronic configuration of beryllium and write the electronic configuration of boron. When you write these two electronic configurations, you will see, when you write the electronic configuration, try to fill in electrons in boxes, orbitals. Fill electrons in the boxes. And you will see now that the explanation you can give here, is that here boron has 4 electrons, it is full. Beryllium has 4, it is full. Boron has 5 electrons. The other 4 are full, but the fifth electron in boron comes from where? The fifth electron to be removed in boron is located in the 2p subshell, which is slightly further away from the nucleus. So we can conclude, because the electron is in the p subshell, which is further away from the nucleus, we can now conclude that the outer electron in boron is shielded from the attraction of the nucleus by the 1s and the 2s electrons, and less energy is needed to remove the electron. Finish. This electron here is outside. So 1s2, 2s2 are shielding it from the attraction of the nucleus. So less energy is needed to remove this electron, and that is why boron has a lower first ionization energy than beryllium. The same thing goes. Why is it that there is a drop of this. Oxygen has a lower ionization energy than nitrogen. We are in period 2. We are still explaining period 2 before we go to period 3. In period 2, nitrogen and oxygen. In period 2, the next thing you do is you have to write the electronic configuration of nitrogen and write the one of oxygen. Now you will see that the 2p subshells are half filled. They are half filled and it gives some stability. But for oxygen, 2 of the orbitals are half filled, but one is full. One has a pair of electrons. And the electron to be removed comes from the pair of electrons. So it takes us to what we call spin pair repulsion. Spin pair repulsion. The electrons that are spinning in opposite direction. There is repulsion between the electrons that are spinning in opposite direction here. So we can now say electron, because the electron being removed in oxygen, the electron that is removed from oxygen is from the 2p orbital, which contains a pair of electrons. In this pair of electrons, there is extra repulsion. There is extra repulsion between the pair of electrons. And when there is repulsion between electrons go further away from each other. And when electrons go further away from each other, there's less energy that is needed to remove the electron. That's it. Now let's go to period 3. Period 3 is from sodium to argon. Then why is it that aluminum has a lower ionization energy, first ionization energy, than magnesium? Aluminum and magnesium, the same thing. It's the same thing we did in period 2. I said write the electronic configuration, and you will now see that in aluminum, the first electron that has to be removed is the 13th electron. If you are removing an electron in a successive way, it will be the 13th electron. So we can now say the 13th electron to be removed from to be the 13th electron, which is going to be for the first ionization energy. The 13th electron to be removed from aluminum is located in the 3p subshell. It is located here in the 3p subshell, which is further away from the nucleus. The nucleus is right down here. So it is further away from the nucleus. Our conclusion, if you were given a paper to answer it, should be that the outer electron to be removed from aluminum. The outer electron to be removed from aluminum is shielded from the attraction of the nucleus by what? By the 2s2 and the 2p6 3s2 electrons, and less energy is needed to remove the electron. If there is space, and depending on the number of marks, if there are more marks, you can say the 13th electron to be removed is located in the 3p subshell, which is further away from the nucleus. Full stop. Then you continue. The outer 3p1 electron in aluminum is shielded from the attraction of the nucleus by 2s2, 2p6, and 3s2 electrons. For that reason, less energy is needed to remove the electron. That's all. The same thing, we have to go for phosphorus. Phosphorus and sulfur, because they'll ask us in the third here that why is it that the first ionization energy of sulfur is lower than that of phosphorus? It's the same thing that we did in period 2. In phosphorus, I said you need to write first the electronic configuration. Now phosphorus has the 3p subshell are half filled. There is some stability there. But for sulfur, even though 2 of the orbitals in the 3p subshells are half filled, electron is going to be removed from where? It's going to be removed from one of the pair of electrons here. And because of this pair of electrons that are spinning in opposite direction, there is repulsion between them. And when there is a repulsion between a pair of electrons spinning in opposite direction, electrons, they go further away from each other. as a result of that repulsion. And when electrons are further away from each other, less energy is needed to pick it up. So we can now conclude that electrons being removed in sulfur is from the 3p suborbital. It's from the 3p orbital, which contain a pair of electrons. There is extra repulsion between the pair of electrons, resulting in less energy needed to remove the electron. I will advise you, learners, you can say because of spin pair repulsion. All what we have explained here is because of is spin pair repulsion. You can write because of spin pair repulsion, then you explain. When the examiner sees that it is spin pair repulsion, because that is the major point. You have a point, they give explanation, you have the other points. And that is how you can do it. We will have to go through it. You should be able to. This is the first energy against plotted against atomic numbers of elements in period 3. You could be given this one in your exam, and you are asked to interpret the curve. This graph like that, you can interpret it. You should know the property that has been plotted against the atomic number and see the trend across the period. You see that, as we have said, there is an increase, the general increase from across the period, but there are some drops. There is a drop after magnesium. There is a drop after phosphorus. So you need to give reason for this drop. Very, very important. Reason for this drop. Very, very important, which I've already explained to you. Okay, another property is variation in melting point and electrical conductivity. Melting point and electrical conductivity. Learners, you should know that melting point and electrical conductivity will depend on the type of bonding. It will depend on the type of bonding. The type of bonding in the compound will determine how the boiling point is, the melting point is going to look like. And then the electrons. Are there delocalized electrons? And the type of bonding there, the type of structure. You should know that as we move from metals, that is from metals to metalloids, and from metalloids to non-metals, there is a change in bonding. We move from giant metallic bonding, metallic bonding to covalent bonding. Metallic bonding to covalent bonding. In terms of structure, we are moving from metallic lattice structure. Or what we call giant metallic structure, to what? To giant covalent structure, or what we call giant molecular structure. Then from this one, we now go from phosphorus. From phosphorus right down, we call them the simple covalent structure or simple molecular structure. Once more, in terms of bonding, we are moving from metals to non-metals. That is, we are moving from metallic bonding to covalent bonding. In terms of structure, we are moving from sodium to aluminum. We are leaving sodium to aluminum. We call that metallic lattice structure, or we call them giant metallic structures. Then silicon. You know silicon, these are metalloids. They have giant covalent structure, or what we call giant molecular structure. And then from phosphorus right down, we call them, they have simple covalent structures, or what we call simple molecular structures. And all these are contributing to their boiling point and to their electrical conductivity. So in that case, in terms of metals, you know that the metals, there is strong electrostatic force of attraction between the nucleus and the sea of electrons, in metals. That is what gives the metals the metallic structure. The metals they have delocalized electrons. Metals have delocalized electrons in their outer shell. We call it sea of delocalized electrons in metals, and that's what makes the metals to conduct electricity. Again, you go to like silicon. Because of the 3D nature of silicon, it makes silicon hard. It makes silicon hard. That is the giant molecular structure or the giant covalent structure in silicon that makes it to be hard and require a high amount of energy to overcome the strong bonding there. Even though the bonding there is covalent, the silicon to silicon, they are all covalent bonds, but it will need high energy to overcome them. Unlike the last category, which is the simple covalent structures or the simple molecular structures, or most of them, some of them are solid, and like chlorine and argon, those ones are gases. They are held together. The molecules are held together by weak intermolecular forces. These are intermolecular forces that exist between those type of molecules. These are weak intermolecular forces. Even though they are strong covalent bond, but the molecules holding, the forces holding the molecules together, like molecules of chlorine, holding chlorine molecules together, holding sulfur molecules together, molecules together, holding phosphorus molecules together. We call them weak intermolecular forces. Then argon is an atom, is gaseous in nature, and the forces holding gaseous molecules together where they are weak van der Waals forces. So all these are contributing to their low melting point. So let's get back to here. So summarizingly, I can say the trend in melting point and the electrical conductivity across a period depends on the nature of bonding and structure of the element. Across period 3, like in this case, bonding is from metallic, as I've explained, metallic to covalent bonding. And they have the structure, and the structures are from the structures here. The structures are from metal lattice, or what we call the giant metallic structure, to giant covalent structure, or what we call giant molecular structure, and finally to simple covalent structure, or what we call the simple molecular structure. So the boiling point will increase from sodium to magnesium and to aluminum due to increasing number of delocalized electrons, telling you that aluminum has a higher boiling point than magnesium, and magnesium has a higher boiling point than sodium. The reason is that you should know that each aluminum atom will donate 3 electrons. When they donate 3 electrons, they will form aluminum 3 plus ion. The same thing with magnesium. Magnesium will form 2 plus ion because it donates 2 electrons. And sodium will only form 1 plus ion because it donates only 1 electron. So for this reason, it makes bonding in aluminum stronger. Bonding in aluminum is more stronger due to the electrostatic forces of attraction between its 3 plus ions and the large number of negatively charged delocalized sea of electrons holding the giant structure together. That is it. For electrical conductivity, you should know that electrical conductivity, as I said, it will depend on the localized electrons. So we can say in aluminum, there are more delocalized electrons. We have 3 electrons in the valence electrons, 3 valence electrons in aluminum. So we can say there are more delocalized electrons available to drift across the structure when aluminum metal conducts electric current. When aluminum metal conducts electric current, it is more than the way magnesium will conduct and more than the way sodium will conduct, because there are more delocalized electrons in aluminum that are available to drift across the structure. In that case, we can say aluminum is a better conductor than magnesium and than sodium. In terms of the melting point here, for the trend here, the melting point for silicon is highest in this period. We can say the melting point for silicon is highest. Silicon has the highest melting point because of a giant molecular structure. We also call it a giant covalent structure. Due to what? Due to the tetrahedral arrangement of the SI bonds. You know that each silicon atom is bonded to each other by strong covalent bonds. So the 3D bonding gives silicon high melting point, high boiling point, and a great hardness, but it is very poor in electrical conductivity because of what? They don't have the localized electrons. So we can say it is poor, even though it is a semi-metal. So we can say silicon is a semi-metal. Yeah, it's a metalloid. It's a semi-metal. Electrical conductivity is very low compared to other metals. Compared to other metals like sodium, magnesium, and aluminum. Let me say electrical conductivity of silicon is lower compared to group 1 and group 1 to group 3 metals. Now we can go now to, after silicon, we are now for phosphorus to argon. Why is that the melting point will increase to, is going to increase to sulfur, then drop down again? I told you that phosphorus, sulfur, and chlorine, the phosphorus and the chlorine, they are all solids. That is why they have a higher, they are all solids. They are all solids. And they are all solids and have simple molecular structure or simple covalent structure, which are held together by weak intermolecular forces. For that reason, phosphorus and sulfur, they have a higher boiling point. But chlorine and argon, they are all gases. And I said they are all gases. And they are held together by weak van der Waals forces. So the molecules together are held by weak van der Waals forces. Even though the covalent bonds between each are held by the covalent bond between each, there is covalent bond between the atoms, but the intermolecular forces between them are weak. Intermolecular forces. They are usually, we call them instantaneous dipole-induced dipole forces. So argon, with their all gases and the forces holding gases together, the forces holding the gases together are what we call weak van der Waals forces. So there are weak van der Waals forces here. There are also weak van der Waals forces. There are also weak intermolecular forces between phosphorus and silicon and sulfur. Just that the nature of their structure, which is a simple covalent or simple molecular structure, it's making them to have the higher melting point. Okay, we will go now to the last one, which will be bonding in the period 3. As we said, we are leaving from metallic, that is from sodium to aluminum is metallic. Silicon we have giant molecular. Then phosphorus, sulfur, and chlorine, they are all simple molecular structures. But argon is still a simple molecular structure, but just that they are gases. They are also held by weak intermolecular, weak van der Waals forces. Chlorine and argon are gases. So once more, when you are given properties like this, when it comes to a melting point and electrical conductivity, please try to figure the type of bonding and the type of structures that are there. When it comes to electrical conductivity, try to figure out whether they have the localized electrons or not. Then, when it comes to the first ionization energy, like in this trend here, when they are talking about the first ionization energy of elements, especially non-metals in period 3 or period 2, for non-metals, please, what you need to take into consideration will be, for non-metal, what you need to take into consideration should be the spin pair repulsion. For example, in nitrogen and oxygen, they drop between nitrogen and oxygen, and they drop between phosphorus and sulfur. The spin pair repulsion is the one that is working. Then, now, other factors that will also influence the ionization energy across the period. One, the general increase in the positive nuclear charge. Because as you go across the period, there is a consistent increase in the number of protons. And this results in a general increase in the positive nuclear charge. And when the positive nuclear charge increases, there is also a decrease in the atomic radius. And when there is a decrease in the atomic radius, the distance between the nucleus and the valence electrons is shortened. And the force of attraction between the nucleus and the valence electrons becomes stronger. For that reason, the valence electrons are pulled closer to the nucleus, leading to what? Leading to a decrease in the atomic radius. And for that purpose, to remove an electron will be difficult, because you will need extra energy to overcome the force of attraction between the nucleus and the valence electrons. Then again, you should know a true definition of the first ionization energy. You must mention the number of moles. You must mention that it is 1 mole. You must mention that it is removed from a gaseous atom. The atom is in a gaseous state. You must mention that it results in an ion which has one plus charge. We call it a unipositive charge. If we are talking of the second ionization energy, you need to mention 1 mole, but you need to put 2 electrons. You need to put 2 plus charge. So the first ionization energy of is defined as the energy required to remove 1 mole of electron from 1 mole of gaseous atom to produce 1 mole of gaseous ion with a unipositive charge, or with a charge of +1. Then again, ionic radius. You should know that the ionic radius, as you move across, ionic radius for cation is decreasing across the period. I gave you the reason, because these cations have lost their outermost electrons. They have lost electrons. They have lost 1, 2, or more electrons from the third principal quantum shell. So they have lost electrons in the third shell. They now have only the first and the second shell. So for that reason, the electrons, the valence electrons are not shielded. There's less shielding. The shielding is less. The shielding of these electrons in the cation here is less. Shielding of this electron in the cation from the attraction of the nucleus is less, because they have already lost their valence electron. And that is why you see them decreasing like that. But in terms of, but for anions, you should know that because they have gained 1, 2, or 3 electrons, their ionic radius is greater than their original atoms. Unlike here, the ionic radius is less than the original atom. The original atoms are bigger than this one. But this one, the ionic radius are what? Are larger than the original atom. Because of what? There's a repulsion. The electron that they are gaining, phosphorus has 3, sulfur has 2, chlorine has 1. That this will cause what? They will cause greater repulsion between the electrons that have been gained. And when these electrons that have been gained, when there's repulsion, what happens? When there's repulsion, there's the radius. When there's repulsion, the radius, or there is expansion in the radius, and that's why it is giving it a larger size than the original atoms. So you should be able to interpret this and interpret your curve. You could be given figures, you could be given symbols like this, or you can draw circles like this or balls like this to interpret. If you are giving curves like this, you should interpret. And then you should interpret why is there a decrease right down here. Why is it that here a P3 minus has the highest one, then it is decreasing and going? There's greater repulsion in phosphorus anion because 3 electrons have been gained, and there's greater repulsion between the different electrons. Here there are only 2 electrons, and here there's only 1 electron. The repulsion is less. So that is the thing. And you should also recall that as you go across the period from left to right, or from metals to non-metals, for atomic radius, not ionic radius this time around, atomic radius, there is a consistent decrease in the atomic radius. Why is there a consistent decrease? 1, as you are moving across, there is a consistent increase in the positive nuclear charge because of increasing number of protons. This nuclear charge does what? It enforces, it increases the force of attraction between the nucleus and the valence electron, or the outermost electrons, pulling them closer to the nucleus, thus reducing the atomic size or the atomic radius. On the other hand, as you move down the group, as you are moving down the group, the atomic radius is instead increasing. Why? The atomic radius, as you go down the group, there is a consistent increase in the number of shells. The shells are increasing by 1. From lithium, that is period, from lithium, okay, this is period 1 here. Now period 1 to period 2. Period 2 to period 3, there is increase. Period 3 means it has 3 shells. Period 2 means it has 2 shells. Period 1 has just 1. Period 4 means it has 4 shells. So there is a consistent increase in the number of shells because of increasing number of protons. And when there's an increase in the number of shells, automatically the ionic radius increases. So learners, you should be able to know this and apply them when asked. Thank you for listening. Please, if you haven't subscribed to our channel, kindly do that, and do not forget to hit the notification bell. Wishing you good luck in your exams.